We're going to start off with the statement of the Pythagorean theorem. The Pythagorean theorem says that the sum of the squares of the lengths of the legs of a right triangle is equal to the square of the length of the hypotenuse. Now this has a lot of words and a lot of clauses, and so typically students think of this in terms of the picture. Let's start with a right triangle. We will label the legs A and B, so the length of this leg is A, the length of this leg is B, and the length of the hypotenuse is C. And so what we want to do is we want to think about the words. The sum of the squares of the lengths of the legs. Well, these are the legs, so the length of the legs are A and B. The sum of the squares of the length of the legs, the sum of the squares of A and B, A squared plus B squared, is equal to the square of the length of the hypotenuse. The length of the hypotenuse is C is equal to the square of the length of the hypotenuse. And this is the formula that most students are familiar with when it comes to the Pythagorean theorem. Now, when we use the Pythagorean theorem in this class, we're just going to be applying it, so we're not going to focus on the proof so much. There are lots of intuitive proofs, graphical proofs that you can see online if you look around for it, but really we're going to focus on the application of it. And when we have those applications, we want to focus on this picture right here. We will always be drawing this picture, making sure that we have the legs and the hypotenuse labeled correctly, so that when we apply the formula, we apply it to the right parts. Our first application of the Pythagorean theorem will be the derivation of the distance formula. Now you may remember the distance formula from a previous math course, but sometimes students in their memories, they get the plus signs and the minus signs mixed up and everything. And so by thinking through the derivation, it gives us the opportunity to fix those things rather than just hope that we've remembered it correctly. So we're going to start off with 2 points. We'll call them x1, y1 and x2, y2. So these are the 2 points, and we are interested in the distance between them. We'll call that distance d. Now, when we look at it in this framework, there's not a lot that we can do, but once we draw in a right triangle, this gives us access to the Pythagorean theorem. The only thing we need to do is determine how long this leg is and how long that leg is, and then we can plug the numbers into the formula. Now, figuring out how long these lengths are is something that actually pulls on knowledge about the number line that goes way, way back to, I don't know, very early in your math careers. So if we look at this point here, the x-coordinate is x1, and this point here, the x-coordinate is x2. And so the question becomes, if we have 2 points on the number line, how far apart are they? So let me just do an actual example here. How far apart are the numbers 5 and 2? Now we could manually count this out, 1, 2, 3, they're 3 apart, but you might also remember that we can determine the distance between two numbers by taking their difference. So 5 minus 2 is equal to 3, and 3 is this distance between them. And so this tells us that subtraction is the way that we determine the distance between two numbers. And so what we can do with that is see that this distance here is x2 minus x1. And the same thing happens in the y direction. That height is y1, this height right here is y2, which means that this length right here is going to be the difference between those two, y2 minus y1. And so now we have a right triangle. This is one leg, that's another leg, and that's the hypotenuse. So, we get the first leg squared plus the second leg squared is equal to the hypotenuse squared, right? The Pythagorean theorem, the sum of the squares of the legs, of the length of the legs of the right triangle is equal to the square of the length of the hypotenuse. And so we have this formula, and we are interested in solving for d. And so to solve for d, we have to just take the square root of both sides. I'm just going to do that right here. Take the square root of d squared, that gives us d, and this is the distance formula. Here's a quick example of an application of the distance formula. Find the distance between the points, -3, 2 and 2, 5. Now, even though it's not completely necessary, I find it's helpful to sketch a picture of the situation. So -3, 2 is right here. So here's -3, here's 2, -3, 2 like that. And then the second point is 2, 5. So 2 this way, 5 this way. So that's point 2, 5. And we're trying to find the distance between them. So when you draw the picture like this, you can see that we've got the numbers labeled on the number line and things like that. And this helps us to understand the whole picture and help us put things together. Sometimes if you make arithmetic mistakes, you won't catch them. But if you look at the picture, things won't quite line up. And so the formula says that the distance between the 2 points is equal to the square root of a bunch of stuff. And you have to remember what the distance formula says. Now, one thing that's really important, and where drawing a picture really helps, is that it gives us the opportunity to label the points. Sometimes when students are reading problems, your brain will scramble these two numbers, and it happens, it's okay. But if you label the points 1 and 2, it helps you to keep your focus and not lose track of things. So it's going to be x2 minus x1 squared plus y2 minus y1 squared underneath the square root. And so this is equal to square root of x2. So we go to the second point and we look at the x-coordinate of the second point. 2 minus x1. So x1 is -3, first point x-coordinate. Squared plus y2, which is 5, minus y1, which is 2 squared. Subtracting a negative is addition, so 2 plus 3 is 5, 5 squared is 25, plus 5 minus 2 is 3, 3 squared is 9, 25 plus 9 is equal to square root of 34. Now we can do a quick check. 34 is equal to 2 times 17, and so there are no square factors there, so we can't simplify that any further. And so this quick calculation using the distance formula, there are a couple things to think about. One of them is this mistake right here. Oftentimes students, if they're going quickly, they'll just do 2 minus 3 and they won't get the right answer. Remember that it didn't come up in this problem, but a negative number squared is positive. That is a mistake that I sometimes see. And over here in this picture, we can actually identify this 2 minus -3 we said is 5. That was this horizontal distance. And when you look at the picture, it makes sense. 5 minus 2 was 3, and that's that vertical distance there, and that also makes sense. And so this is how having the picture can sort of help make sure we don't make mistakes. And so the distance between these 2 points is the square root of 34. One quick observation about this problem. If we were to label the points differently, so this point is point 1 and this point is point 2, and we were to work it out, it will still give us the same answer. So this distance is equal to x2 minus x1 squared plus y2 minus y1 squared, square root of all that. It's equal to square root of x2. So this is our point 2 now. The x-coordinate is -3. -3 minus 2 squared plus 2 minus 5 squared. It's equal to the square root of -5 squared plus -3 squared. And since a negative squared is positive, we have 25 plus 9, which is still square root of 34. So even though we numbered the points differently, we still ended up with the same answer. And all of this comes down to the fact that if you swap these two numbers, x2 minus x1, if you swap the numbers, you'll get the negative of the previous answer. But since when you square it, it becomes positive, it all sort of washes out in the end. Another application of the distance formula is the derivation of the equation of a circle. Now we say the equation of the circle sometimes, but other people prefer to say the standard form of a circle because in fact circles have lots of different representations and this is only one of them. It turns out to be extremely useful because it tells us a lot of information about the circle. Well, what is a circle? A circle is the set of points x, y that are some fixed distance r away from some fixed point. In this case, we'll call this point here hk. xy is a generic point representing all the points on the circle, and r is the radius, or the distance between the center to any point on the circle. So if we look at the distance formula, we have that the distance between any 2 points is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. Now for this particular application, what we're going to do is we're going to square both sides of this equation. So when we square, we eliminate the square root. And we get d squared on this side. So in our setup right here, what is the distance? Well, the distance is that amount r. x2 minus x1. Well, we have to decide what our point 1 and our point 2 is. Traditionally, we'll call the center our point 1 and the generic point xy point 2. And so x2 minus x1, well, that's just the letter x minus h squared plus y minus k squared. Now convention, you usually see it in the other order, x minus h squared plus y minus k squared equals r squared, but they're both the same thing. And this is the formula for the standard form of the formula for a circle centered at the point hk with radius r. Here is our first example of an application of the equation of a circle. Find an equation for the circle centered at the point 5, -3 with radius 4. Now in this case, you're given the two pieces of information directly. The two pieces of information that you need are always going to be the center and the radius. In this case, we know explicitly center is 5, -3, and the radius is 4. And just as a reminder, the notation in the formula is that that's the point h comma k, and this is the letter r. And the formula says that the equation of a circle is x minus h squared plus y minus k squared is equal to r squared. And so in this case, it's just a matter of plugging in the values. We know the h is 5. We know the k is -3. So if x minus 5 squared plus y minus -3 squared is equal to 4 squared. And so if we simplify this, subtracting a negative is adding. Y plus 3 squared is equal to 16. Now there are a couple things about this formula that you need to pay attention to. First of all, in this problem, you're just asked to find the equation of the circle. You don't need to actually find values of x and y. The second thing about this is that your center is the point hk. Now even though you think of this as an xy coordinate, this x and this y in this formula, they represent a generic point on the circle. The h and the k, those are your fixed points that represent, or your fixed values that represent the center of the circle. So sometimes students end up trying to solve for x and solve for y and doing all sorts of crazy things because they're sort of in a mindset of just trying to do stuff. The thing you want to pay attention to is that you answer the question. Find an equation for the circle. Equations of circles look like this. And so if you don't end up with something that looks something like this, you've probably made a mistake. Find an equation of the circle centered at the point 1, -2 that passes through the origin. Now, if you aren't familiar with this language here, the origin is the point 0, 0 in the plane. Now, as we said last time, we need to find two pieces of information. We need to know the center, and we need to know the radius. Now, in this case, the center is given to us explicitly. But the radius, if we read through the words, the problem doesn't give us a radius, and so we have to go figure it out. So what we can do is we can sketch a quick little picture here. The point -1, 2 is right here, and we have a circle that goes through the origin, through the point 0, 0, something like that. And so from this, we know that the radius is going to be that distance. Now, what is that distance? Well, there are a number of ways to do it. We could go all the way to the distance formula and just call this the point 0, 0, call this the point -1, 2, and plug it all in. Or we can think about the Pythagorean theorem and think about the lengths of these things. This side has length 1, that side has length 2. Regardless of how you do it, if you work this out, that r value, so let me write down the Pythagorean theorem. Well, let me just write this out. 1 squared plus 2 squared is equal to r squared. And so that r value is going to be, well, got 1 squared plus 2 squared is 5, so square root of 5 is equal to r. So the radius is the square root of 5. Now that we have the center and the radius, we can just plug it into the formula. X minus h squared plus y minus k squared is equal to r squared. Let's put a little line here to separate those out. And so x plus 1 squared, right? So minus a negative is plus y minus 2 squared is equal to the square root of 5, but we're going to square that, so it's actually going to be 5. Now this right here is a mistake that students often make. They often forget to square the radius, and so they'll just write square root of 5 because they see radius. Remember that it's the radius squared. And that's something that's really just a matter of paying attention and slowing down and making sure you think about the whole problem, think about the whole formula. A more advanced problem that we might run into is to determine the intersection of a line and a circle. Now, if we think about it, the intersection of a line and a circle, there are three things that can happen. First thing that can happen is that there are 2 points of intersection. Next thing that can happen is that there are no points of intersection, so the line and the circle just don't intersect. Third thing that can happen is that the circle and the line intersect at a single point. We call this being tangent to the curve. That's a word that you're going to run into, especially if you go on and take some calculus. You're going to see lots of stuff involving tangent lines. But tangent means basically that it just comes up and touches it at that one point. So these are the three different situations. Now, we won't know in advance which situation we're in. What's going to matter is that when we go through the algebra will tell us what situation we're in. And we'll see that as we look at the examples. So here's our first example. Find the points of intersection between the line y equals x plus 1 and the circle centered at the origin with radius 3. Now, what is our overall strategy going to be? Well, the general strategy that we're going to have is that we need to have two equations, and we're going to try to substitute one into the other to solve for x and y. Now, in this case, we only start with one equation, the equation of the line, y equals x plus 1. We have a description of the circle, but we don't yet have the equation. So that's the first thing we need to do. Now, just as before, we need two pieces of information to get the equation of a circle. We need the center and the radius. And fortunately, we're told this explicitly. The center is at the origin, the point 0, 0, and the radius is 3. So we put this together into the formula for a circle. We get x, well, technically it's going to be x minus 0 squared, but since x minus 0 is just x, we're going to leave it like this. X squared plus y squared is equal to 3 squared, which is 9. And now we have this equation for our circle and this equation for our line. And we see that this is of the form y equals something, so we can take that y and substitute it into here. X squared plus, x plus 1 squared is equal to 9. Now we're going to need to do some algebra, so let's expand out the binomial, x squared plus 2x plus 1. And now we're going to move everything to one side of the equation and combine like terms. So we've got 2x squared plus 2x, subtract 9 from both sides. 1 minus 9 is negative 8, so minus 8 is equal to 0. And in this case, we could also divide this by 2. And we can see that we're left with a quadratic equation. Now we have to think, well, what are the methods we can use to solve quadratic equations? Well, one of them is factoring, another one is using the quadratic formula, or if you're feeling really fancy, you could try to do completing the square. Now in this case, when we look at this, we might quickly identify that factoring is probably not going to work, so that leaves us with either completing the square or the quadratic formula, and most students tend to go for the quadratic formula. Completing the square is useful and has its applications, but in this case, the quadratic formula is probably the easiest way to go. So here's our quadratic equation. X squared plus x minus 4 is equal to 0. Now we're going to use the quadratic formula, so we need to identify the a, the b, and the c in that formula. So ax squared plus bx plus c. So our a is 1, our b is 1, and our c is negative 4. Now everything is just a matter of execution. X equals negative b plus or minus the square root of b squared minus 4ac, all of this divided by 2a. b, okay, so b is 1. So negative 1 plus or minus the square root of b squared, which is 1, minus 4ac. So 4 times a is 4, and then times c is negative 16. So minus a negative is plus 16 over 2, which is negative 1 plus or minus the square root of 17 over 2. So this gives us our x-coordinates. However, we are trying to find the points of intersection, which means we also need to find the y-coordinates. Now we have a couple options. We could go to the circle formula and plug into that. It turns out to be super messy, but instead it makes much more sense to use this formula right here because it's already of the form y equals something. So y equals negative 1 plus or minus the square root of 17 over 2. There's our x plus 1. We have a little bit of fraction arithmetic to do here. Negative 1 plus or minus the square root of 17 over 2. We need to find a common denominator, so plus 2 over 2. And now that we have a common denominator, we can go ahead and do the arithmetic. I'm actually going to squeeze it in over here. So negative 2 plus 2 is plus 1. 1 plus or minus the square root of 17 over 2. Now, at this point, a lot of students will just stop. But we haven't yet stated the points of intersection. We have some x values, we have some y values, but we need to pull it all together to get the points of intersection. So, what are our points of intersection? We'll take the plus case first. So negative 1 plus square root of 17 over 2. 1 plus the square root of 17 over 2. And the other point when we take the minus case, so negative 1 minus the square root of 17 over 2, comma, 1 minus the square root of 17 over 2. And these are the 2 points of intersection. Notice how in this problem, the problem told us there would be 2 points of intersection. When we did the quadratic equation, we ended up with 2 separate values. This is what we mean by the algebra will tell us what's going on. And if we were to look at the picture, just sketch this real quick. Circle of radius 3, actually move to this side. Circle of radius 3, the line y equals x plus 1 goes up like this. So you can see that there's a point of intersection over here and another point of intersection over there. And so those are the 2 points of intersection. Here's another example. Find the x-intercepts of the circle with radius 5 centered at the point 2, 5. Now in this case, when we look at the problem, we have no equations given to us. We have to work it all out. So let's first think about the picture. What are x-intercepts? X-intercepts are points along the x-axis that intersect the circle, or intersect whatever graph we're talking about. Now in this case, we have the circle of radius 5 centered at 2, 5. So here's 2, here's 5. So there's our center, and the radius is also 5. And so if we go down 5, we're going to go here, and that's going to be something like this. And of course, the top half of the circle as well. Now, what's interesting about this is we can see immediately where that point is, but we should also go through the process of solving it. The other thing is that we can see from the picture that it's going to be tangent, because if we're 5 away, 5 up from the x-axis and you have a circle of radius 5, it's just going to barely touch at that one point. And we'll see all of this come out of the equations. Now, the question is, well, what is the line? The line is this line right here. That's the line y equals 0. And so in this case, knowing that we're finding x-intercepts are the points that intersect with the curve intersects the line y equals 0. And so that's our first line. And now our second equation is going to come from the circle. So I'm going to squeeze it up here. We have center, we have radius. The center is at the point 2, 5, and the radius is 5. And so therefore the equation is going to be x minus 2 squared plus y minus 5 squared is equal to 25. Let me make sure that's on the screen before I keep going. Okay, that fit. Perfect. So here's our formula. Now we're just going to plug things in. Y equals 0. We're just going to drop it right in. So x minus 2 squared plus 0 minus 5 squared is equal to 25. 0 minus 5 is negative 5. Negative 5 squared is positive 25. So x minus 2 squared plus 25 is equal to 25. Subtract 25 from both sides. X minus 2 squared is equal to 0. Take the square root. X minus 2 is equal to, technically this is plus or minus the square root of 0, but since plus or minus the square root of 0 is the same thing, it's just 0. We just have one case. And this right here is where the once again, the algebra is telling us what's going on. The algebra tells us that there's only one point of intersection because we have plus or minus the square root of 0. If this were some other value, we might have 2 points of intersection. Or if this happened to be a negative value, it would be plus or minus the square root of a negative number. And then we'd say that there are no points of intersection because we're not going to deal with imaginary numbers when we're talking about intersections of curves on the line, on the plane. And so our x value is 2. We already have y equals 0 explicitly, so the intersection is 2, 0. So the x-intercepts of this circle are at this one point right here, 2, 0. And it's the only one. Most students are already familiar with the concept of angles. However, it's important for us to go through the terminology just to make sure we have the right ideas and the right words. So, what is an angle? Well, an angle is what you get whenever you have two line segments that intersect. We call this point right here the vertex. And usually when we're talking about measuring an angle, we're measuring from one side to another. So in this case, we'll go this way. The from side is the initial side. And the to side is going to be the terminal side. And this is just language that gives us from one side to another. Typically, we call the angle something like theta. Theta is a Greek letter. And so when we're measuring an angle, we're measuring how much rotation it takes to go from one to the other. So from the initial side to the terminal side. Now, in general, those angles can appear anywhere in the plane in any orientation whatsoever. We sometimes call them geometric angle when we're just saying, okay, the measure of the angle between these two things. However, there's a specific way of orienting things on the plane that's particularly useful for trigonometry. And this is known as standard position. So standard position, when you have the xy plane like this, the initial side is along the positive x-axis. And then the terminal side is wherever it happens to be. When we have angles in standard position, it makes sense to talk about positive and negative angles. So positive angle is an angle, positive angle. A positive angle is an angle which rotates in the counterclockwise direction. So from here to here in this direction is a positive angle. Negative angle will rotate in the clockwise direction, so from here down to here. And this will become important later on as we start talking about more trigonometry stuff to know whether we're talking about positive and negative angles and sort of how everything is oriented on the plane. There are two units that we use to measure the size of an angle, degrees and radians. Now with degrees, most students are familiar with this, the idea that if you go one full rotation, that's the same as 360 degrees. Now, why 360? Why is that the number? It turns out that this is a number given to us by history. It has its usefulness in that this number has a lot of divisors, meaning that I could divide this by 2, 3, 4, 5, 6, 8, basically a lot of small numbers and not end up with the decimal. So most students know that a right angle is 90 degrees. And it would have been grossly inconvenient if this number were like 73.8. It just wouldn't work well. And so for convenience, this number 360 degrees has been chosen because it has all these nice divisors. Now, this is both good and bad. It's good in the sense that it works. Practically speaking, this gives us nice numbers for a lot of these angles, and it works. It's bad in that this number 360 is still arbitrary. It could have been 720, and it would have even more divisors. So why this one instead of something else? Again, that's just sort of given to us by history. So what mathematicians want to do is they want to try to take this idea of an angle and measuring the angle and relate it back to straight geometry rather than using arbitrary values like this. And so the way we do this in math is we say, okay, well, here's an angle. And let's imagine we go out some radius r and create a circular arc like this. The distance along that arc we'll call s. And this is our angle theta. And what we're going to do is we're going to define theta to be s over r. Now this may seem strange at first. This why this arbitrary r and why this distance here. Well, this gives us the same concept. When s gets bigger, the angle gets bigger as long as we keep the same radius. And so this at least captures the idea of bigger angles have bigger numbers. The fancy part about this is that this actually works regardless of what value of r we use. The same angle for different radii. So instead of using the whole thing, if we use either of these smaller angles here, the ratio of s over r remains the same for the same angle. And so this is what we mean by having a geometric definition. It's dependent only on the shape of the geometry and some geometric facts about the shapes, and not dependent on some arbitrary value like 360. And this is, when we go on later on, we'll actually see that this gives us a lot of formulas that are nicer looking and easier to use and easier to understand. And so we'll get to that in a little bit. So now we have two different ways of measuring angles. We have degrees and we have radians. And the question is, how are these two things related to each other? This relationship right here, 360 degrees equals 2 pi radians, is the fundamental relationship that we need to keep in mind. We talked last time about the 360 degrees in a circle, but what about 2 pi radians? Where does that come from? Well, if we think about a circle, you might be familiar with the formula circumference is equal to 2 pi r. Circumference is the distance going around the circle, and r is going to be the radius of that circle. Now, if we think back to last time, theta equals the distance traveled divided by the radius of the circle. We can use this picture. If we go one full trip around the circle, our theta is going to be s over r. Well, that distance s, is just the circumference. 2 pi r over r equals 2 pi. And so one full trip around the circle, one full rotation, is 2 pi radians. So now that we have this relationship, the question is, how does this help us convert between the two? Well, the most common way to think about this is the application of what's known as a conversion factor. We can take this thing and turn it into two fractions, 360 degrees, over 2 pi radians. And this will equal 1, and that's by dividing both sides by 2 pi radians. Or if we divide both sides by 360 degrees, we get this, 2 pi radians over 360 degrees. And so to convert from degrees to radians or radians to degrees, you have to multiply by the correct conversion factor to make sure that your units cancel out. One side note about these units. Radians, technically speaking, are what are known as a pure unit. They're just a number, and that's because we have distance over distance here. But it is helpful to write the word radians when you're talking about angles so that you don't get confused just seeing 2 pi floating around on its own. Reminding yourself that you're talking about an angle here. So we will tend to write the word radians here, even though it's strictly speaking not necessary. For our first example, we're going to convert 330 degrees to radians. Now, the way we use our conversion factors is that we need to multiply our value by the appropriate fraction to make the units cancel out. So in this case, these 330 degrees, the degrees are on top, and so we need to have degrees on bottom. So 360 degrees on the bottom. 360 degrees is the same as 2 pi radians, so we put that on top. From here, it's just a matter of arithmetic. Now you can multiply the tops first and then try to reduce, but I'm going to reduce first because it makes our life a little bit simpler. So we think about 330 divided by 360? Well, we can divide out the 10, so we have 33 over 36 divided by 3, so that's 11 over 12. So 11 over 12 times 2 pi radians. The 2 and the 12 reduce even further, so we have 11 pi over 6 radians. Now, I use the conversion unit 2 pi radians over 360 degrees because that's the fundamental relationship. Some students prefer to just use pi over 180 degrees, so pi radians over 180 degrees, because this has already been reduced. That's perfectly acceptable. Either one is fine. I just use this to emphasize the point that the fundamental relationship is 360 degrees is 2 pi radians. For this example, we're going to convert radians to degrees. Specifically, we're going to convert pi over 3 radians to degrees. Now, the same idea applies. We're going to multiply by a fraction to make the radians cancel out. So we have radians on top, so we want 2 pi radians in the denominator, so that's the same as 360 degrees on top. So now the radians cancel out. Now, as we said before, technically these radians are pure units, and so they actually don't appear, but it really is helpful to write that down. So radians cancel out, the pi's will cancel out, and if we look at the denominator, we have a 3 and a 2. 3 times 2 is 6, so 360 degrees divided by 6 is going to be 60 degrees. Now, one mistake that students tend to make is that as soon as they see pi's, they assume they are in radians. This is something that is generally true in applications, but you need to be careful of it. It is possible for us to have something like pi degrees. And it's also for us to have something like 3 radians, where there is no pi. And so don't fall into the trap of assuming that, oh, if it's pi, it's in radians, and if it's not pi, then it's not in radians. That's not quite how this works. You should think of this specifically. Pi is a number, and if we're talking about a measurement, we're either going to say radians or we're going to say degrees. And you have to be able to follow that language and not just focus on the pi. When we're talking about angles, there's an important concept we need to think about, which are known as coterminal angles. Now, coterminal, the prefix co, means together. And so you can think of words like cooperate, to operate together, or to work together. So coterminal angles are angles that end together. Now, implicitly, it means that they also start together. So if we have some initial side and some terminal side, coterminal angles are angles that start from the same initial side and end at the same terminal side. So how can we get lots of different coterminal angles? Well, it depends on how we measure. So here's one way of measuring this angle. Alternatively, we could have gone in the negative direction and measured it that way. And if you think about it, we could actually go even further. We can do a full loop around and then end up at this angle. And so these are lots of different ways we can get the same angle, we can measure the same angle, but get different results. And so when we say that we have coterminal angles, we're saying that these angles are related to each other, same initial side, same terminal side, even though we get different measurements. Now, the nice part about these measurements is that they are all related to each other in a very clear mathematical way. If we're talking about degrees, then this angle right here from here to here, and this angle right here from here to there, those are 360 degrees apart. And you can sort of imagine if we try to create this negative angle, if we go up to this positive angle, and then go backwards, go one full loop in the negative direction, that's how we would get this angle. And that one full loop is subtracting 360 degrees. Same thing happens in radians. With radians, you're going to be adding or subtracting multiples, integer multiples of 2 pi. And so two angles are coterminal with each other if their difference is an integer multiple of some complete measurement of a circle. So either 360 degrees or 2 pi radians. Here's an example using coterminal angles. Find an angle coterminal with 19 pi over 4 on the interval from 0 to 2 pi. Now, a couple quick words about this. The book will often do this. It will just say 19 pi over 4 without saying radians. This comes back to the idea that radians are technically not even a unit. It's just because you have a ratio of length over length, so it's just a pure number. But typically, I would try to encourage you to say radians here, even though it doesn't say so. Now, the important thing about that is that it's not radians because of the pi. It's radians because it's not degrees. If you see a degree symbol, then it's definitely in degrees. If you don't see it, then it's definitely in radians. And so that's how you tell the difference between the two measures. The interval from 0 to 2 pi, well, that's one full rotation. And so we're looking for the angle sort of measured in the positive direction, the smallest positive solution, or smallest positive angle that matches up with this one. Now, there are a couple of different ways of doing this. You can do it geometrically. I'm going to do this algebraically, because later on we're going to see a more geometric approach to this. 19 pi over 4. Now, to find another angle that is coterminal with this, we can either add or subtract 2 pi. Now, in this case, this number is a big number, so we're trying to get ourselves down to this interval from 0 to 2 pi, so we're going to subtract 2 pi. So 2 pi, and this is going to be 19 pi over 4 minus 8 pi over 4. Find a common denominator. That's 11 pi over 4. Now, some students are quick to say, okay, well, therefore, the answer is 11 pi over 4. You have to think about what these numbers actually represent. 11 fourths. What is 11 fourths as a mixed number? 11 fourths is 2 and 3 fourths. And that's still bigger than the 2 pi over here. So 2 and 3 fourths pi is bigger than 2 pi. And so we're not done yet. We have to make sure we actually end up in this interval. So we're going to have to subtract off another 2 pi. 11 pi over 4 minus 8 pi over 4, which is equal to 3 pi over 4. Now, this fraction 3 fourths is less than 2. So 3 pi over 4 is less than 2 pi. And this will be the final answer. This is the angle that is coterminal with 19 pi over 4 on that interval. We're going to take a moment to talk about the unit circle. Now, the unit circle is a circle of radius 1 centered at the origin. Now, also when I say the unit circle, a lot of students bring to mind this diagram that has a whole bunch of numbers here. And we also have a version of this that's in radians that we'll look at in a moment. Now, I don't want you to memorize this. I don't want you to brute force memorize all these values, because that's not actually the way we like to use the unit circle. That's the way that you just sort of do it to get through some tests and then forget it later. What's better to do is actually think about this and understand the relationships between the different parts of the circle. Now, the unit circle diagram has special angles listed on it. These angles are the common values that we use, and we're going to evaluate functions known as the sine and cosine functions on it later. But right now, we're just going to focus on these angles. And rather than thinking about all these angles, we just want to focus on these two right here, the 30-degree angle and the 45-degree angle. Because using these two angles, we can actually generate the rest of this diagram. So let's look at this. So 30 degrees. And what we're going to do is we're just going to march our way around the circle in units of 30 degrees. So 30 degrees, the next one's 60 degrees, 90, 120, 150, 180, 210, 240, 270, 300, 330. The 30-degree angle is 1/3 of a right angle. So 1/3 of 90 is 30 degrees. And so if you just take that 30 degrees and march it all the way around the unit circle, that will get you the majority of these values. And you could do the same thing with the 45-degree angle. The 45-degree angle is half of a 90-degree angle. So 45, 90, and just add multiples of 45 going around here. So 135, 180, 225, 270, 315, and 360. And so this gets you the entire way around the circle using the 45-degree increments. And that will get you the rest of the values on this chart. So again, rather than memorizing this whole thing, just focus on the angles 30 degrees and 60 degrees. And then as you march your way around the circle, you can fill out the rest of these values. Here's the exact same unit circle picture, except with the angles measured in radians. Now again, we're going to focus on these two right here. So pi over 6 is the same as 30 degrees, and pi over 4 is the same as 45 degrees. And all we need to do is follow the exact same process, but now we also have to think in fractions. So pi over 6, 2 pi over 6, and then 2 over 6 reduces to 1/3. 3 pi over 6, 3 over 6 is 1/2. 4 pi over 6, 4 over 6 reduces to 2/3. 5 pi over 6, 6 pi over 6, 7 pi over 6, 8 pi over 6, 9 pi over 6, 10 pi over 6, 11 pi over 6. And so if you just go by multiples of pi over 6 all the way around the circle, remembering to stop 3 times around each quadrant, you're going to get all of these values. And that's way easier than trying to memorize these. And all you would need to do with the pi over 6s is just reduce at every step if you can. Same thing will happen with the pi over 4. So pi over 4 is halfway to a 90-degree angle. So pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4. And so again, brute force memorization is not the way to go. If you just think about the patterns and think logically through this picture, you should be able to get all of these values. So here's an example that we've seen before. Find an angle coterminal with 19 pi over 4 on the interval from 0 to 2 pi. Now, what's different in this approach is instead of last time where we just subtract 2 pi's until we get into this interval, we're actually going to think about this geometrically using the unit circle. So we'll sketch the unit circle here. And this will work whenever this denominator is a 2, 3, 4, or 6, because those will be the denominators that we'll be working with in the unit circle diagram. And so, since there's a foreign denominator, we're going to look at the angle pi over 4, which is the same as 45 degrees. And what we're going to do is we're just going to work our way around the unit circle, just like when we were filling in the values, except we're just going to keep on going until we get to 19 pi over 4. So here's 1 pi over 4. This is going to be 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4, and this would be 8 pi over 4. I'm not going to keep on writing, I'm just going to keep counting. 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. And so using this diagram this way is a little bit easier conceptually to think about rather than just this calculation using these pi's that you may not have that much intuition with yet and dealing with fractions. All we need to do is just count out on the diagram because this is one of our useful values that we see on the unit circle diagram. So remember the denominators of 2, 3, 4, and 6, and I guess also integer multiples of pi, although those are much simpler. We can use a unit circle diagram and just think about it and work our way around the diagram to get an angle. We're going to be thinking about the arc length of a circular arc. What does that mean? We're going to start off with just a circle. A circular arc is any portion of the circle of a fixed radius r where this thing traces out part of that circle. And that's what we mean by a circular arc. Now, circular arc will be, the word is subtended by an angle theta. That tells you sort of the angle, this interior angle right there. This is called a central angle if you want to be super specific about that. So anyway, the question is, how long is that length of arc if we have some angle theta here on some circle of radius r? Now there are two approaches to this. The first approach is going to be, we're just going to use some logic and basic deductive reasoning to get there. And the second way is going to be a more formal mathematical way of looking at it. So using logic, let's sort of think about this. We know that the entire circle is going to have a length, an arc length of 2 pi r. That's because That is what's known as the circumference. The circumference is the distance going all the way around the circle. And so let's say we have an angle theta here. Well, if we're working in degrees, this theta is going to be some measure, let's just say, I don't know, maybe 60 degrees or whatever. But if we think about it, this is a proportion of the whole circle. So if this were 60 degrees, it would be 60 degrees out of the possible 360 degrees to go all the way around. And so for the arc length, in radians, or excuse me, in degrees, what we're going to have is going to be this angle divided by 360. So it's going to be this fraction of the whole circle, or this proportion of the whole circle. I'm going to put degrees here. And so when you do some simplification, the 2 is going to reduce 360. You're going to have theta times pi times r over 180 degrees. And this is the formula that we use when we're in degrees. Now, you can see that this formula, it doesn't look particularly nice. It's just, it's kind of messy. It's got a fraction in it, and it's got 180 degrees in the denominator. Let's do this again in radians and see what happens. So, just as before, circumference is still the whole same thing. But now, instead of thinking about theta in degrees, we're going to think about theta in radians. This is theta out of a possible 2 pi radians to go all the way around. So the proportion this time is going to be theta out of 2 pi. And we're going to multiply this by 2 pi r, just as we did here, because this is the distance going around the whole thing. So you have a proportion of the whole circle. And now this time, when we reduce, the 2 pi's cancel out, and this gives us a nice formula. S is equal to theta times r. And so this gives us the arc length given an angle either in degrees or in radians. This gives us the length of the arc subtended by that central angle. Now this formula right here is actually really close to the mathematical definition, the mathematical approach. You might recall that we defined the angle in radians to be theta is equal to S over r, where S was the arc length and r was the radius. And we said theta was defined by this value. And if you just rearrange this, multiply both sides by the r, you get r times theta is equal to s, which is exactly this formula down here. And so this kind of shows us how the mathematical approach makes things a lot easier. We set ourselves up with a good definition of what an angle is. And because of that, we have a nice formula for what the arc length is. And all it is just a rearrangement of this formula. So here's an example of a problem that uses arc length. The high roller at the link has a radius of 260 feet. How far has a cart traveled if it rotates 30 degrees? So for those of you who don't know, the high roller is the Ferris wheel on the Las Vegas Strip. Has a radius of 260 feet. And this thing is going to rotate 30 degrees. Now, it doesn't matter where it starts because the circle is the same all the way around. So we're going to start wherever I drew this thing, and we're going to say it's going to rotate by 30 degrees. And the question is, how far has it physically traveled as it moves along that arc? We're going to look at this problem in a couple different ways. We're going to start off by using just the formula. So formula for arc length. When we have arc length in degrees, this is going to be theta over 180 degrees times pi times the radius. And so you can see we just plop the numbers in. So this is going to be 30 degrees over 180 degrees times pi times 260. Now there's not a lot that we can do here. We can reduce some fractions. So this reduces to a 1/6, and we can try to reduce it with the 260. This turns out to be divisible by 2 but not 3. So 260 over 6 is going to be 130 over, there's going to be 1/6. So 130 over 3 pi. Now this number by itself isn't great to use. If you tell someone 130 thirds pi, they're not going to know what that is. We can do a little bit of work by just trying to simplify this a little bit. So if we reduce the fraction or write it as an improper fraction, we can see that this is going to be something like 43 1/3 times pi. But that still isn't a great value. We would like to know what this thing is, because when we measure physical units, we tend to want to have some sort of strict, some sort of numerical value here. And so if we can plug this into a formula, or plug this into a calculator, we'll get the number 136.13, and this will be in feet. So this way of approaching it is just plug into the formula, don't think, just plug in and go, and you'll get this value down here. What are other ways of looking at this that may help build our intuition? Well, first of all, one thing we need to do is build intuition with radians. And so we can think of this and convert this to radians. 30 degrees is the same as pi over 6, and then use the radian formula, which is s is equal to theta times r. This right here, this is going to be, we said 30 degrees is pi over 6 radians, so pi over 6 times 260. And if we actually do this calculation here, that's exactly the same values we got here. It's just that we didn't have as much reducing to do with the fractions and so forth. We still have to work from here and get the rest of the way. But at least in this first step, we have a simpler looking fraction. We can also think of this 30 degrees as being 30 degrees out of a total of 360 degrees. So this is 30 degrees over 360 degrees, which is not about, this is 1/12. And so we can say, well, we want 1/12 of the distance going around the circle. And so use that fraction there instead of this reduced form. It's sort of a little bit more, builds a little bit more of the intuition. A similar idea is the area of the sector of a circle. Now, what is a sector of a circle? Well, the sector of a circle, if we think about cutting out a wedge, almost like a pie-shaped wedge, this right here is a sector of the circle where this is at the center. And so the area of this thing is the area of this pie-shaped wedge that we have right here. We're going to look at this the same way as we looked at the other example, which is we're going to think about this as proportions. We know that the area of the entire circle is equal to pi r squared. So what happens? Let's say that this is an angle theta. Let's label this radius r. And so if we use the same proportion, for the area of the sector, I'm going to write A sub s, area of the sector. This area is going to be equal to, well, we're going to use a proportion of the whole circle. So we'll start with degrees as before. So theta over 360 degrees times pi r squared, right? So again, a proportion of the area of the circle, and that proportion is measured out by this angle here. If we did it in radians, this would be theta over 2 pi times pi r squared. And again, you'll notice that because this pi appears here and here, that this reduces, and this gives us a nicer formula for the area of a sector when we're dealing in radians compared to when we're doing it with degrees. In degrees, we're stuck with this 360 degrees in the denominator. This one's just theta over 2. It's a little bit nicer, but the pi's go away. Here's an example looking at the area of the sector of a circle. A lawn sprinkler sprays a distance of 20 feet and rotates through an angle of 60 degrees. What is the area of the sector of grass the sprinkler waters? So here we have a sprinkler head that's going to turn back and forth between these two angles. It's going to be a 60-degree angle here. And we're interested in the area of this sector, and this has a radius of 20 feet. Now, once again, we could use either formula, but this time we're going to sort of focus on the radian value because that's the one that's going to take more practice. Because otherwise, we're just plugging this into a formula and not really thinking. So, what is the area of the sector? So the area of the sector when we have radians is theta over 2 r squared. Let's think about 60 degrees. Now, for 60 degrees, that you could go back to the unit circle picture and see what it is, or we could just sort of think about it. And I'm going to practice the thinking process. The key value to remember is that 30 degrees is pi over 6. And so if we have 60 degrees, that's 2 times 30. 2 pi over 6 is the same as pi over 3. And so this is equal to pi over 3 over 2 r squared. Now, fraction inside a fraction, you have to multiply by the reciprocal, so this is going to be pi over 3 times 1/2 r squared. The r value is this 20 feet right here, and so actually let me put that in right here. 20 squared is 400. So now we have to multiply this out and see what we get. So the 2 reduces with the 400 gives you 200. We get 200 pi over 3, which again, this isn't so helpful in a practical problem because no one looked at that and immediately can say, oh, I shouldn't say no one can, but typically when people are given a number like that, they don't know what area that actually represents. And so what we need to do is we need to plug this into a calculator. And if we plug it into a calculator, put the answer over here, you get the answer 209.44 square feet. And so this sprinkler sprinkles an area of almost 210 square feet. This is a course in trigonometry, but there are a lot of useful physics applications of these ideas, and so it's worth taking a little bit of time to talk about some of the physics ideas. In particular, we're going to focus on linear and angular velocities. Now, we're not going to get into a big argument about whether we mean velocity or speed here, because that's one of those physics subtleties that's not worth it for this class. But we are going to think about what we mean by this. So, a linear velocity. What do we mean by linear velocity? Well, think about going and driving your car, you're going 70 miles per hour. So 70 miles per hour. And if we think about that per, meaning like division, we can set this up as a fraction, 70 miles per hour. Now how many hours? Per 1 hour. And so this sets up this ratio, miles per hour, and we have 70 miles per hour. And so linear velocity is going to be this form. It's going to be a distance over a time, which we could write as d over t, or sometimes you'll see this as s over t, just depending on who's doing the writing. So this formula here sets up our concept of velocity. Velocity is a ratio of distance over time. What would an angular velocity look like? Well, an angular velocity, instead of thinking about distance, you're going to be thinking about angle, how much spinning you do in some amount of time. And so the way we write this is like this. Omega is equal to angle over time, and angle is typically denoted by a theta, so theta over t. This right here looks like a W. It's actually a Greek letter omega. And so some students will call it W. It's really an omega. It's a Greek letter. And that sort of keeps us consistent. So we have Greek letter here, and we use Greek letters for talking about rotations and things like that in this setup. Now this angle right here, something that's very important for this class, is that the angle we're going to use will always be in radians. We always want the angle in radians, and that will help simplify our formulas, and so we don't have to worry about chasing units around and things like that. If you're given the angle in terms of degrees or in terms of rotations, you're going to have to convert those values into radians. So one rotation is 2 pi radians. 360 degrees is 2 pi radians. And you use that conversion to make to convert the values for these problems. In some situations, the angular velocity and linear velocities are actually related to each other. The best way to think about this is to imagine a wheel. A wheel is spinning, but as it spins, that spinning translates into a linear velocity as it moves down the road or down the street or down whatever place this is traveling. And so there's definitely this relationship here. Now there's more to this relationship than just the rotation and the linear velocity, because the radius is going to matter. Let's call that radius 1, call that radius 2. Let's say that these wheels are rotating at 1 rotation per second. Which one is traveling faster? Well, in 1 second, this will do 1 full rotation, which is the distance is 1 full trip around the circle. And that circle, that distance around that circle, is bigger than this 1 trip around this circle. Another way to think about this is to actually make the linear speeds the same and think about how this affects the angular speeds. So the linear speed, let's say that these two things are going the same linear speed. The smaller wheel has to spin faster to keep up with the bigger wheel. A non-circular version of this is to think about adults walking with little children. When an adult is walking, they have to take fewer steps relative to the little kids. The little kids have to move their legs a lot faster to keep up with the adults. And so this is another way of looking at this relationship between the size and the linear and rotational velocities. So here's what we have to do now. We have to figure out how these things are mathematically related. And so let's start with the linear velocity. So velocity is equal to how far it travels per amount of time. This S right here, if you think back to the example we just talked about, this S corresponds to an arc length. How far around this circle have you traveled in some amount of time? And so rather than using S, we can actually relate this back to the angle using the arc length formula. S is equal to R times theta. Right? And so now we have this setup. Velocity is R times theta over t. This ratio, theta over t, angle per time, that is an angular velocity. And so in fact, this is R times omega. And that gives us our fundamental relationship, velocity is omega times r. And this relationship right here also captures everything that we said before. If we have the same rotational speed, but we have different radii, the bigger radius corresponds to a bigger velocity. If we have the same linear velocities, then the bigger radius has to have a smaller omega, and the smaller radius has to have a bigger omega, and that corresponds to the picture that we have up here. So these are how linear and angular velocities are related to each other, and this is the formula we're going to need to understand in order to do the problems. So here's a typical sounding example that mixes the linear velocity and the angular velocity. The high roller has a radius of 260 feet and completes one loop in 30 minutes. How fast in feet per minute does the ride move? So again, we've got a little Ferris wheel here, and let's say we start at the bottom, and it completes one full loop in 30 minutes. So 30 minutes for one loop. Now remember that for these problems, we want to be writing everything in terms of radians because that makes our formulas a lot simpler. So one loop, instead of thinking about one loop, we should think about that in radians. But one loop, one revolution is going to be 2 pi radians. And once we have this set up, we can think about the formula. Velocity, linear velocity is equal to angular velocity times the radius. So the radius we had was 260 feet. That's from the problem right here. And we just need to think through what the angular velocity is. Remember, angular velocity is the amount of rotation per amount of time. So the amount of rotation is 2 pi radians per amount of time. The amount of time is 30 minutes. And then we're going to also multiply that by the radius, which is 260 feet. Oops. If we think about the units here, remember that the radians are a pure unit. So in the final answer, they're not going to show up. And we have feet per minute, which is the exact same units we want in this problem. Feet per minute. And the rest is just to do the calculation. So 2 pi over 30 times 260. If we do some manipulation, we'll cancel out the 10. 2 times 26 is going to be 52. So it'll be 52 pi over 3 feet per minute. Now again, this value with pi written in it, this mathematical expression, doesn't really help us understand. So instead, we're going to plug this into a calculator. And when you do, you get the value of 54.45 feet per minute. What does this mean? So every minute that goes by, the cart moves about 55 feet. And that answers the question. How fast does the ride move? The ride moves 54.45 feet per minute. we're going to talk about the sine and cosine functions on the plane. Now, if you've taken trigonometry before, you might remember sine and cosine functions involving a bunch of right triangles. We're not going to do that presentation just yet, but we'll get there. In the meantime, it might be useful for you to try to think about how what we're doing here is related to the ideas you remember from your past. So anyway, what are we going to do? We're going to start off by thinking about the xy plane. Now, if we put an angle in standard position, like this, the question is, how are we going to define our functions cosine theta and sine of theta? Now, if you haven't even seen these functions before, these are just functions that are important to trigonometry, and we're just trying to build out what this thing could possibly mean. And so what we're going to do with this is we're going to imagine some point x comma y that lies on that line segment going out from the origin. Now, it doesn't matter which point we use as long as we don't use the origin, because whatever point we have, we can draw a circle of radius r that goes through it. And now this is starting to set up the ideas that we're going to need for the sine and cosine functions. First of all, the value of r. What is the radius of the circle? Well, by either looking at the distance formula, or in fact this equation for the circle itself, x squared plus y squared equals r squared, we can get the value of r. And once we have the value of r, we can get cosine theta and sine theta. Cosine theta is defined to be x over r, and sine theta is defined to be y over r. Now you'll notice that we had to pick a point that's not the origin, because if we pick the origin, we're going to be dividing by 0, and none of these are defined. You could also see that geometrically, if we picked our point at the origin, then there's no angle that's been defined from that point. And so this is the setup for the sine and cosine functions. We could do this in another way, where we start with the point x, y, and then build the circle, and then build the angle, and it will still give us the same final picture. So here's an example. The point 3, 4 creates an angle theta in standard position. Calculate cosine theta and sine theta. So what does this mean? If we draw our coordinate plane, the point 3, 4 is right here. If we connect this point to the origin, we create an angle in standard position, and that's called theta. Now our task is simply to calculate sine theta and cosine theta. Now, if we look at this, we can calculate this value r by looking at the right triangle that we create right here. This side has length 4, that side has length 3, and you might recall that this is a 3, 4, 5 right triangle if you've seen that before. Otherwise, you just plug it into the Pythagorean theorem. But we get, in any case, r is equal to 5. And everything from here is just a matter of plugging into the formula. Cosine theta is equal to x over r. This x value here is, well, that point was 0.34, so the x value is 3. This is 3 over 5. And sine theta, which is y over r, is equal to 4 over 5. And that's pretty much all there is to calculating the sine and cosine functions when it's set up in this way. I wanted to make two quick observations about this problem that we just completed right here. The first one is that we never actually calculated the angle theta. In this whole process, we calculate sine of theta and cosine theta, but we still don't actually know what that angle is. Now, if we stare at the picture, we can do some basic geometry. If we look at this, it's more up than horizontal, so that makes it look like the angle is bigger than 45 degrees. There are a few observations we can make like that, but we don't know the value of the angle. And that's something that you're going to have to get used to, this idea that this value of theta is just floating around out there. We don't know what it is other than from its representation here. Yes, there is some numerical value that if we were to go measure it, we could actually calculate. But for a lot of times, we just end up saying, well, whatever this angle theta is, it has these properties. Sine of this angle is this, and cosine of the angle is that. The second observation I wanted to make is that for this angle theta, we could have picked a different point to create a different triangle, but the sine and cosine theta values will still be the same. So if we had picked the point, let's say 6, 8, which sort of doubles this point, moves it up here, and we write out these fractions will reduce to the same thing. And so that's a very important fact about the sine and cosine functions, is that it depends only on the angle, and so not the specific triangle that you've created. We're going to think a little bit about the sine and cosine functions and the quadrants of the plane. Now here are the definitions again. Sine of theta is y over r, and cosine theta is x over r. And the thing to observe about this is that value of r is always positive. That means that when y is positive, the sine is positive. When y is negative, the sine is negative, and same with the cosine in x. So let's think about the implications of that observation. So here's the xy plane. Now, if we are on this side of the y-axis, we will have x is greater than 0. We'll have x is greater than 0 down here as well. And if we're on this side of the y-axis, we have x is less than 0. Now, if we think about the y values, y positive is the upper half of the plane. So here, y is bigger than 0. Here, y is bigger than 0. And then when y is negative, you're on the lower half of the plane. Y is less than 0. Y is less than 0. But from the observation we made previously about the sine and cosine functions, this actually tells us everything we need to know about the sine and cosine functions. Cosine theta, if theta is in the first quadrant, is going to be positive, and sine theta is going to be positive in this first quadrant. In the second quadrant, if we look at this, we're going to see that cosine theta is negative, and we're going to see that sine theta is negative. Down here, we can say cosine theta is negative and sine of theta is negative. So this is quadrant 3. And then quadrant 4, cosine theta is positive and sine theta is negative. And so this is really interesting because what it means is that by looking at whether the sine and cosine functions are positive or negative, we actually know what quadrant the angle is going to be. So if we have them both negative, we're going to be in quadrant 3. If cosine is positive and sine is negative, cosine positive, sine is negative, we're in quadrant 4. And so this is a useful geometric relationship to keep in the back of your head as we look at sine and cosine functions of various angles. The Pythagorean identity is an important identity in trigonometry. It should not be confused with the Pythagorean theorem. The Pythagorean theorem is about right triangles, and the Pythagorean identity is about the sine and cosine functions. Now, they are related, but they are not the same thing. So if you're asked to state the Pythagorean identity, you should not be talking about the Pythagorean theorem. You should be talking about the Pythagorean identity, which is the sine and cosine functions. So what is the Pythagorean identity? We'll write it down first. Sine squared theta plus cosine squared theta is equal to 1. Now when we write sine squared theta like this, we actually mean sine of theta quantity squared. Putting the square there is a mathematical convenience. It's actually easier to read when things get more complicated. So just get used to that idea right now. Sine theta squared is the same as, I should say, sine of theta squared is the same as sine squared theta. Okay, so this is the identity. The question is, well, what does it say? Where does it come from? Well, let's just make the substitutions and play around with the algebra. So we know that sine of theta is y over r, and cosine theta is x over r. Now if we square the fractions, we get y squared over r squared plus x squared over r squared is equal to 1. Clear the denominator, we get y squared plus x squared is equal to r squared. But more typically, we write the x first, so x squared plus y squared is equal to r squared. So what is this thing saying? This is actually the formula for the circle centered at the origin of radius r. This was the circle that defined our functions, right? We had a point xy, had a radius r, and an angle theta. And so what this statement is actually saying, it's just a reflection of the fact that our sine and cosine functions are built out of a circle. And so the Pythagorean identity is a way of stating that using just the sine and cosine functions. One of the interesting things we can do with the Pythagorean identity is that if we know the value of sine or cosine, we can find the value of the other function as long as we have one more piece of information. So let's take a look at this example. Suppose that sine of theta is equal to -1/2 and theta is in the fourth quadrant. Determine cosine of theta. Well, let's think about this for a moment. First of all, in our xy plane, we know that our angle is somewhere in the fourth quadrant. Now, it doesn't matter which way we label it. We could label it, think about theta going this way in the positive direction, or we can think of it going in the negative direction. Either one is fine because it only depends on where that terminal side lies. So what do we have? We have sine of theta is equal to -1/2. Okay, so sine of theta is equal to -1/2. And we have sine squared theta plus cosine squared theta is equal to 1. Then it seems like we should just be able to plug this in. So sine squared theta, so sine of theta is -1/2 squared plus cosine squared theta is equal to 1. Square that out, negative squared is positive, so 1/4 plus cosine squared theta is equal to 1. Subtract 1/4, we get cosine squared theta is 3/4. Take the square root of both sides. Cosine theta is equal to plus or minus the square root of 3/2. And now here we have to do a little bit more thinking. We're pretty close. We have it down to one of two possible values, plus square root of 3/2 or minus square root of 3/2. And to figure out which one it is, that's where we need that extra piece of information. The angle is in the fourth quadrant. Because in the fourth quadrant, we know that the x value is positive. And since the x value is positive, cosine is positive. And so we should be using here, cosine of theta is the positive square root of 3. I shouldn't say the positive square root of 3, plus square root of 3/2. And so we need to use the two pieces of information. First piece of information is the value of the sine function, which lets us plug in and get us close. And then the second piece of information is by knowing which quadrant the angle is located in, we can determine whether we want the plus sign or the minus sign. In order for us to take our next step into trigonometry, we need to introduce the concept of a reference angle. For an angle theta in standard position, the reference angle of theta is the acute geometric angle it makes with the x-axis. Now the word acute here, an acute angle is an angle between 0 and 90 degrees, or 0 and pi/2 radians. Geometric angle means that we're just going to use the positive measurement and not worry about what direction, whether it's a positive angle or a negative angle. We're just going to call it a positive angle. And so the geometric angle makes with the x-axis. So let's take a look. Let's say we have an angle somewhere over here in the second quadrant. Now if we look at it, the angle that that line makes with the x-axis looks like that. That right there, this is the reference angle. Right, so our angle theta could be over here. This is some angle between 90 and 180 degrees, but the reference angle is this acute angle right here. And so as a practical example, let's just consider what is the reference angle for a 210 degree angle. So first we have to think about 210 degrees to figure out what quadrant it's in. So it's between 180 and 270, so it's going to be in quadrant 3. And so this angle right there is 210 degrees. Everything from here is just a matter of looking at the geometry. Now there are formulas you can memorize for this. I'm not even going to bother writing them down because they're not worth it. Just sort of look at the picture and think about it. If this is a 210 degree angle, how big is this angle right here? Well, we know that it's 180 degrees to this point, and so from here further, you need to go an additional 30 degrees. And so the reference angle for the 210 degree angle is 30 degrees. And we get this by just looking at the geometry. Sometimes you're going to subtract, sometimes you're going to add. It's just looking at the picture and thinking it through. we want to think about the relationship between these reference angles and the unit circle. Now, the unit circle is just a circle of radius 1 centered at the origin. So this is a radius 1. And we like thinking about the unit circle for the sine and cosine functions because it makes the denominator equal to 1. So remember that sine of theta is equal to y over r, and cosine theta is equal to x over r. And if we just pick that r to equal 1, then we're going to have that this is equal to y and this is equal to x. And so if we pick some point xy on the unit circle, it creates an angle theta. And we can calculate its values by just looking at the x and y coordinates and not having to worry about that denominator because the denominator is 1. And so here's the set that we have. The question is, what do reference angles do for us? Well, it turns out that we can use reference angles to take the first quadrant and understand all the points on the entire unit circle by just using geometry. So what does that look like? Well, let's say for a moment that we're interested in taking this thing and reflecting it across the y-axis this way. The angle theta ends up being down there. That angle is the same as this angle by reflection. And in fact, this point, if we think about it, if we reflect across the y-axis, the y-coordinate does not change, but the x-coordinate becomes negative. And so that becomes our point, negative x comma y. And now, because this angle here is theta, we can actually look at the angle in standard position. We'll call this thing alpha for a moment. Squeeze that in right there. This angle alpha creates a reference angle theta. And so if we know the reference angle theta, we can actually get sine of alpha and cosine of alpha. Let's just think about that. Sine of alpha. Well, this point right here, sine of alpha is equal to y. The y coordinate, because we reflect it horizontally, is unchanged. So sine of alpha is equal to y. Cosine of alpha, it's the x coordinate, which in this case is negative x. So it's the negative of whatever that one is. And so reference angles allow us to bounce this point from the first quadrant into the second quadrant. And we can do the same thing vertically. We can reflect these things down into the third and fourth quadrants. So if we do a vertical reflection there, we'll see that the reference angle theta goes here and here. Forgive me for them not being very accurate, but this sets us up with this rectangle of points. Down here we have negative x, negative y. Here we have x, negative y. And so by looking at the various angles here, the same reference angle can be used to get all the values for the sine and cosine functions in all the other quadrants by doing this reflection property and just thinking about where the points go. Before talking a little bit more about trigonometry, we're going to take a quick detour and talk about some special triangles. Now, these special triangles are important to trigonometry, but the stuff we're going to learn is actually things you could have learned a long time ago. All you need to know are some basic facts about triangles and the Pythagorean theorem. So what are the two special triangles that we're going to look at? First one's going to be the 45, 45, 90 triangle, and the second one is the 30, 60, 90 triangle. Now these numbers, 45, 45, 90, they correspond to the angles of the triangle. So in this case, we have a right angle here, that's our 90, and these two angles are both 45 degrees. And you'll notice that they add up to 180 degrees, as they should, because these are triangles. And so from this, what we're really interested in are the lengths of the sides of this thing. Now, because of the fact that this is an isosceles triangle, because of the symmetry, this is S and that is S, and we are interested in finding that length over there. Well, this is just a quick application of the Pythagorean theorem. S squared plus S squared is equal to C squared. So 2S squared is equal to C squared. C is equal to the square root of 2 times S, but we actually write this as S squared of 2. We took the plus case because we're talking about a geometric length, so we'll never talk about a negative geometric length like that. And this rearrangement right here, this is one that you're going to want to get used to. we put the s on this side of the square root so that we don't accidentally confuse it for being under the square root. You can see that if this line is a little bit too long, this might look like the square root of 2s as opposed to the square root of 2 times s. That's just a notational thing to help you avoid mistakes. So that sets up the relationship between the sides of these triangles. So if this side is going to be s squared root of 2. We're specifically going to be interested in when the hypotenuse has length 1. And in order for this picture to have hypotenuse length 1, we need the value of s to be 1 over the square root of 2. And if we do that, we can actually just replace those values right here. This will become a 1. And s is 1 over the square root of 2. 1 over the square root of 2. Right, and with a little bit of rearrangement, this can be written as square root of 2 over 2, rationalizing the denominator. And so there you go. So this is the 45, 45, 90 triangle, and the values that we are interested in are when the hypotenuse has length 1, the two legs have length square root of 2 over 2. Now for the 30, 60, 90 triangle, we're going to set up things in the similar sort of way. We're going to have, this is going to be our 60 degree angle, this is our 30 degree angle, and there's our right angle here. So how do we find the lengths of this thing? Well, it turns out that with a little bit of creativity, we can actually put this into a framework that lets us get access to the sides. Because right now, the geometry on its own doesn't tell us anything. However, if we take a copy of this thing and put it over there, this is also a 30 degree angle, which means the whole thing is a 60 degree angle, and this becomes an equilateral triangle. And so this is what gives us access to figuring out the lengths of the various sides. So now if this side is length s, then this side over here, well, it's going to be half of the side, but since it's an equilateral triangle, all the sides have the same length. And so this is going to be s over 2. And then we can use the Pythagorean theorem to get the third side. I'm not going to write it all out, but basically what we get here is that this is going to be square root of 3 over 2 times s. And just as before, we are interested in when the hypotenuse has length 1. So we set s equal to 1. I'm just going to redraw it down here this time. So if this is a 60 degree angle, and that's a 30 degree angle that has length 1, when s is 1, this becomes 1/2, and this becomes the square root of 3 over 2. All of these values, the square root of 2 over 2 for the 45 degree, 45, 45, 90 triangle, and the square root of 3 over 2 and 1/2 for the 30, 60, 90 triangle, these are going to be the important values that we're going to need looking at some trigonometric functions in a moment. So we're now going to put these special right triangles together with the unit circle picture to actually find some coordinates on the unit circle itself. So you can see that I've labeled our triangles here with the lengths, and I also have these physical manipulatives that fit over these pictures pretty well. Anyway, the idea now is that if we're given a particular angle, we should be able to determine the coordinates as long as they are these special angles on the unit circle. So let's do an example. Let's take the angle 210 degrees, which is this one down here. What are the coordinates of that point? Well, we first go and think about the reference angle. What is the reference angle for this one? Well, as before we saw, it's 180 degrees plus 30 degrees more, so this reference angle is going to be 30 degrees. And what that means is we could take our triangle here, take the 30 degree angle, and stick it over the top of that. And this tells us exactly the horizontal distance and the vertical distance we must travel to get to that point. Square root of 3 over 2 this way, and 1/2 down, matching up with our values here. And so from this, we actually know the coordinates of this point. This point has coordinates negative square root of 3 over 2, comma 1/2. Negative, whoops, comma, negative 1/2. Negative because we're going in the negative x direction, and the negative y direction as well, so negative, negative. What this means then is that cosine of 210 degrees, cosine of 210 degrees is the x-coordinate on the unit circle corresponding to the angle 210 degrees. This is negative square root of 3 over 2, and sine of 210 degrees is negative 1/2. And because of these particular angles that we've chosen, we can always use one of these two triangles to get every single one of these angles. So the 30-degree angle, 45-degree angle, 60-degree angle. Over here in the second quadrant, we can use the same triangles, but we're going to think about the reference angles. That's a reference angle of 60, reference angle of 45, and reference angle of 30. And you just trace that all the way around the circle. Every one of those angles is related back to a reference angle that is either 30, 60, or 45 degrees. And so from this, we can get all of these coordinates. Now, I'm not going to write them all out because it's going to take a while for us to do that. I will put a graphic up that has all the angles and all the values listed. But this is one, again, where you can try to brute force memorize all these points. And, you know, if you can memorize them correctly, good for you. But it's much better to be able to think about the picture and understand how these things go together rather than just blindly memorizing information. We're going to do one more sample calculation involving an angle on the unit circle. Calculate sine of 7 pi over 4. So let's just try to construct this from the beginning. We have our unit circle here. We are interested in the angle 7 pi over 4. Now you might remember that pi over 4 is the same as 45 degrees. So pi over 4 is here. We want 7 of those. So 1, 2, 3, 4, 5, 6, 7. So 7 pi over 4 looks like this. And this angle lies in the fourth quadrant. That immediately tells us that the sine value is going to be negative because we are below the x-axis. Our y value is negative here. And now we just have to remember our 45, 45, 90 triangle. This has square root of 2 over 2, square root of 2 over 2, and 1. So this is how it fits into the unit circle, and this is our 45-degree angle. There's our 90-degree angle, 45-degree angle. So we just think about this triangle, and we shove it into this part right here so that the reference angle, we'll call this one the reference angle, just put that, flip it over, rotate it into there. That tells us that both this horizontal length and that vertical length are root 2 over 2. Since we're interested in sine, sine is the y-coordinate. That y-coordinate in this fourth quadrant is negative, so negative square root of 2 over 2. So you can see that we can get this value by thinking about our 45, 45, 90 triangle and just thinking about the quadrants. And again, this is much easier than trying to memorize the entire unit circle diagram. I mean, yes, if you have that, it's quick to just look it up, but it's much more important to be able to use your logic and reasoning skills to determine this value than just looking it up on a table. Because we can relate all the values on the unit circle back to the first quadrant, it's particularly useful to know the first quadrant values for the sine and cosine functions. And so this is a chart that you can basically memorize, and it'll help you to build out everything else. The fortunate thing about this is that there are certain patterns that exist. So when we build out our chart, we have our two functions, the sine function and the cosine function. And then in the next few slots, we're going to put the different angles. So we're going to start with 0 degrees, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. Now again, you should recognize these two from the 30, 60, 90 triangle and the 45, 45, 90 triangle. So that sort of tells you all these values here. But you should also know these values in radians. So this one's 0, that one's pi over 6, this is pi over 4, this is pi over 3, and this is pi over 2. Conveniently, they are all pi's in the numerators, and they count down from 6 to 2, so large denominator to smaller denominator, 6, 4, 3, 2. So what's the pattern for these values? Well, the one you want to remember is that sine of 0 is equal to 0, and then you're just going to count up 1 over 2, root 2 over 2, root 3 over 2, and 1. By some magic coincidence of mathematics, this 1 is also the square root of 1. And if you look at the 1 over here, square root of 4 over 2. That sort of completes the pattern. So this is root 1 over 2, root 2 over 2, root 3 over 2, root 4 over 2. Why it works out this way, I really don't know. It just does. And so that's one of the sort of magical things about this chart. To get the cosine values, it's the same list of values, but swapped into order. So 0, 1 over 2, root 2 over 2, root 3 over 2, 1. And so this is a chart that you will want to be able to write down very quickly to just help you have that information down on paper when you're doing problems. You can always go back and rederive these things by thinking about the unit circle and the 30, 60, 90, and 45, 45, 90 triangles and put it all together again. And you should be able to do that. But having these values at hand is a lot faster and will serve you in the long run to know these things inside and out. So far, we've only talked about the sine and cosine functions. It turns out that there are actually a total of 6 different trigonometric functions that we're going to work with. And it turns out that these other 4 that we haven't talked about yet can all be determined using the same setup that we already have. So remember, we have a point x, y, and once you have that point, you have a distance r from the origin to that point, and that line segment creates an angle theta in standard position. And our sine theta value is y over r, cosine theta is x over r. All these other 4 functions are just other relationships between x, y, and r. So tangent theta is y over x, cosecant theta is r over y, secant theta is r over x, and cotangent of theta is x over y. Now it'll take some time to get used to saying those names, but with a little bit of practice, it'll be pretty easy. Now when we look at these relationships, initially we can start to look around and see some reciprocals. So for example, that's a reciprocal, that, and other relationships like that. But the ones that we're going to focus on right now are actually relating all 4 of these new functions back to just sine and cosine. And all this is just a little bit of algebra. So let's take a look. Tangent of theta. Tangent of theta turns out to be sine theta over cosine theta. So let's sort of think through what happens. If we do sine theta over cosine theta, we have y over r over x over r. And those r's end up canceling out, so you just have y over x. Similarly, if we do cotangent of theta turns out to be cosine theta over sine theta. These last two, cosecant and secant, they end up just being reciprocals of sine and cosine. So the cosecant theta is 1 over sine theta, and secant theta is 1 over cosine theta. And so what this does is this shows us 2 things. First thing is that it shows us that all of these trigonometric functions are related back to the same basic picture. The second thing it shows us is that these 4 new trigonometric functions are related back to the sine and cosine functions. So this shows us a relationship on how all these trigonometric functions are related to each other. So here's an example. Calculate tangent of 45 degrees. We're going to do this 2 different ways. We're going to do it once using the geometric method and once using a more algebraic method. So, the geometry, tangent of 45 degrees. What are we thinking about geometrically here? Well, geometrically, we're thinking about the plane, and we're thinking about this 45-degree angle. Now, on the unit circle, that 45-degree angle corresponds to a specific point. And this is where you're going to have to think back a little bit to the special triangle, so 45, 45, 90 triangle in this case. For the 45, 45, 90 triangle, that side has root 2 over 2, and that side has length root 2 over 2, and that gives us the coordinates of this point, root 2 over 2, comma, root 2 over 2. Now that we know the coordinates of this point, we can just use the formula. Tangent theta is equal to y over x, which is root 2 over 2 over root 2 over 2. Now when you deal with fractions inside of fractions, which we're going to do a lot of in this section, you multiply by the reciprocal of the denominator, so 2 over root 2, get a bunch of cancellation. The final result is 1. So tangent of 45 degrees is equal to 1. The alternative way is to think about the sine and cosine functions and those relationships. Right, so tangent of theta is sine theta over cosine theta. So specifically, if we set theta to be 45 degrees, tangent of 45 degrees, sine of 45 degrees, cosine of 45 degrees, we can calculate sine and cosine of 45 degrees. Now, for that, you can use either your memorized values from the unit circle, or you can just do the geometry here. Either way, you get the same result, root 2 over 2 over root 2 over 2, which is 1. So here we reconstructed the entire triangle, and here we relied on memorized values to do the more algebraic approach. So here's another example. Calculate secant of 5 pi over 6. Now there are a couple things we can do to get started. First of all, let's just figure out where 5 pi over 6 is as an angle. Now you might remember that pi over 6 is 30 degrees, so 5 pi over 6 is 150 degrees. We're going to keep writing these out in radians for practice, but 5 pi over 6 is there, which means that we have to think about what this reference angle is right here. Well, that reference angle is going to be pi over 6, or 30 degrees, and so that just completes the pi going from here all the way to there. Now we have to think about what is the value of the secant function. Well, for the secant function, we have either the formula, so secant of theta is equal to r over x, or we have secant theta is equal to 1 over cosine of theta. Now in both of these cases, we still need to figure out where the point on the unit circle is that corresponds to this angle. You can look that up on the unit circle picture, or the unit circle diagram, or we can just use reasoning and try to figure it out. Because we know the reference angle there is going to be pi over 6, which is 30 degrees. So there's a 30 degree angle, there's a 60 degree angle. We can just use what we know about these values. Let me erase that to give myself some space here. For next to the 30 degree angle, that's going to be square root of 3 over 2, and this has length 1/2. The only catch is that since we are in the second quadrant, we know that the x value is going to be negative. And so, using the top version, secant theta is, oops, let me write that again. Secant of 5 pi over 6 is equal to r over x, where our radius r is 1. X is going to be negative root 3 over 2. Fraction inside of fraction, multiply by the reciprocal of the denominator, negative 2 over square root of 3. Or we can do secant theta, or secant 5 pi over 6 is equal to 1 over cosine of 5 pi over 6. To calculate cosine of 5 pi over 1 over 5 pi over 6, we use the reference angle and adjust the sign, so that's a negative cosine of pi over 6, right? So it's in the negative direction, and that is our reference angle, pi over 6. And that leads us to the same result, negative 2 over the square root of 3. So again, lots of ways that we can think about this, and it's important to be able to think about all these different ways because they're all related to each other. It turns out with all these additional functions, we get additional Pythagorean identities. So first of all, the basic Pythagorean identity, sine squared theta plus cosine squared theta is equal to 1. We're going to use this to derive two more. And the way we're going to derive those things is we're going to divide the whole thing by sine squared theta, and then divide the whole thing by cosine squared theta. So let's do the first one here. So sine squared theta plus cosine squared theta equals 1. And what we're going to do is we're going to divide each term by sine squared theta and take a look at what it gives us. So sine squared theta over sine squared theta is 1 plus cosine squared theta over sine squared theta. Well, let's think. Cosine over sine. Cosine over sine is cotangent. So this is cotangent squared theta. And I got lazy with my parentheses. And then 1 over sine squared theta. Well, 1 over sine theta is cosecant theta. So it's cosecant theta squared, like that. And this is another version of the Pythagorean identity. And all we're going to do is we're going to do the same thing except divide through by cosine squared theta. So again, sine squared theta plus cosine squared theta equals 1. Divide everything by cosine squared theta. And now we just simplify. Sine over cosine is tangent theta, so that's tangent squared theta. Cosine over cosine is 1, is equal to 1 over cosine, which is secant squared theta. Now, one of the nice features of this is that we now have relationships by pairs for all 6 trig functions: sine and cosine, tangent and secant, cotangent and cosecant. And so these are the 3 versions of the Pythagorean identity. We're going to do a quick review of all of the algebra and all of the geometry of the trigonometric functions that we have. So we start off with a point xy on the plane that's not the origin. We have a distance r from the origin to that point, and we have an angle theta that this creates. That gives us the 6 basic definitions for trigonometric functions. Sine is y over r, cosine is x over r, tangent is y over x, cosecant is r over y, secant is r over x, and cotangent is x over r. All these functions are for the specific value of theta that we get from this diagram. From this, we can then do a bunch of algebra to verify these identities. Tangent theta is sine theta over cosine theta, cotangent theta is cosine theta over sine theta, secant theta is 1 over cosine theta, and cosecant theta is 1 over sine theta. And then on top of that, we have the Pythagorean identity, sine squared theta plus cosine squared theta equals 1. This came out of this picture by recognizing that the point xy lies on a circle of radius r. So x squared plus y squared equals r squared, and you divide through by the r squared, and you can relate this back to the sine and cosine functions. With this identity, you can then calculate these other 2 trigonometric identities by either dividing by sine squared theta or cosine squared theta. There's even more to the picture than this. And so what I'm going to do is I'm going to scoot over and draw a coordinate plane. And let's just think about this coordinate plane for a moment. Remember that we thought about where the sine and cosine functions were positive or negative. So we had cosine of theta was positive in the first quadrant, as was sine of theta. So both sine and cosine are positive in the first quadrant. In the second quadrant, cosine is negative, but sine is still, is still positive. In the third quadrant, they're both negative. And in the fourth quadrant, cosine theta is once again positive, and sine theta is negative. Knowing these relationships, it turns out that you can determine for each of the trigonometric functions where they are positive and where they are negative. Now there is a quick mnemonic device for keeping track of this information. It goes like this. There are all sorts of different phrases you can use, but the typical one is all students take calculus, going around from quadrant 1, 2, 3, and 4. All are positive in the first quadrant. Sine is positive in the second quadrant. Tangent is positive in the third quadrant. Cosine is positive in the fourth quadrant. And if it's not listed here, it's negative. So tangent and cosine are negative here. Here, sine and tangent are negative. And then with the reciprocals, you can then find out the rest of these, whether these are positive or negative, based on the fact that when you take the reciprocal, the sign doesn't change. So if sine is positive here, that means that cosecant is positive here. And if tangent is positive here, that means cotangent is positive. And so all of this relates back to the geometry of the coordinate plane. The quadrants are determined by whether y is positive or negative. X and y are positive or negative in each of these quadrants, which corresponds to cosine and sine being positive and negative. Once you have those things, you just take these formulas right here, and you can just apply. So for example, tangent, if they have a sine is positive and cosine is negative, tangent will be negative because positive divided by negative is negative. So there you go. This is how all this information relates to each other. So let's do an application of this. If tangent theta is 2/7 and theta is in the third quadrant, determine cosine of theta. Now we can do this with an algebraic approach, or we can do it with the geometric approach. Let's start off with the algebraic approach. Tangent theta is equal to 2/7. Theta is in the third quadrant, determine cosine theta. So what does it mean to use an algebraic approach? It means that we're going to look at the identities and make substitutions to try to calculate the values. So the first thing that we may try here is use the fact that we have this Pythagorean identity, tangent squared theta plus 1 is equal to secant squared theta. Now we can see that this is going to be useful because secant is 1 over cosine. So these two are related to each other, and we know the value of tangent theta. So what we're going to do, we just plug it in. So 2/7 squared plus 1 is equal to 1 over cosine squared theta. 2/7 squared is 4 over 49 plus 1 is equal to 1 over cosine squared theta. If we add these together, we get 53 over 49 is 1 over cosine squared theta. If we take the reciprocal of both sides, we get 49 over 53 is cosine squared theta. And from here, if we need cosine theta, we're going to take the square root. Cosine theta is equal to plus or minus the square root of 49 over 53. Now we have to do the plus or minus here because remember when we take the square root of both sides of the equation, we introduce that and we have to determine whether we want the plus or the minus. And to get that, we have to think about this third quadrant. In the third quadrant, the x coordinate is negative, which means cosine is negative, which means we want the negative sign here. So cosine of theta is equal to negative 7 over the square root of 53. And so this is the algebraic approach to determining the value of cosine theta given the tangent of theta. We're going to do the same problem again, except now we're going to do a geometric approach. So once again, if tangent theta is equal to 2/7 and theta is in the third quadrant, determine cosine of theta. So for the geometric approach, we're going to start off by drawing a coordinate system. Now theta is in the third quadrant, so we're just going to stick it out somewhere down here. It doesn't have to be exactly proportional, this is just getting the ideas across. And then we know that tangent theta is equal to 2/7. Tangent of theta, if we go back to the basic formula, tangent of theta is y over x, and we know that this is equal to 2/7. Now, you might immediately say, okay, so y is 2 and x is equal to 7, but that would put us in the first quadrant. And so in order to get this point into the third quadrant, we have to take the negative of both the top and the bottom, because negative 2/7 is the same as negative 2 over negative 7. And this gives us a coordinate, y is equal to negative 2, x equals to negative 7, and that coordinate is in the third quadrant. So x is negative 7, y is negative 2. And so this point corresponds to our angle theta. At this point, we want cosine of theta. Cosine theta is x over r. Well, we have our x coordinate right here. But what we don't have is we don't have the r value. Remember, the r value is the distance from our point to the origin. Well, to get that, we use the distance formula. R is equal to the square root of -7 squared plus -2 squared. That's our x squared plus y squared. 49 plus 4 is 53, square root of 53. And so we can just plug it in, square root of 53. Now, the algebraic approach and the geometric approach are two different approaches to the same problem. It is not that one is better than the other, but in fact, it would be best if you can understand both ways of doing it. Proving mathematical identities is going to be one of the hardest things that you do in this course. The reason why is because it relies entirely on your ability to do algebraic manipulations correctly and consistently. One little algebraic mistake throws everything off. And it's very obvious when we're grading papers when someone's faking it, because there are some steps that just don't make sense logically and don't make sense algebraically. And so this is something that will take a lot of time and practice, but if you do all the exercises and put in the time and the effort, you will be okay. If you try to fake it, you're just not going to make it. So this is one where I really want to emphasize the value of doing the exercises slowly and carefully, and being honest with yourself when you're trying to fake it, because it's very clear from the grading side when you are. Okay, so proving an identity. What does that really mean? You're going to have some sort of equation where you're going to have the left-hand side is equal to the right-hand side. And the basic approach to proving an identity is to start from one side and go to the other. So you can start from the left-hand side, do algebraic manipulations to this to make your way to the right-hand side, or you start from the right-hand side and work your way to left. Now, the basic heuristic for this is typically that you start with the more complicated side and try to make it simpler, because the more complicated side gives you more hints as to what sorts of manipulations you might need to make. I will say that there is another method here where you sort of meet in the middle, but for this level of work, this isn't one that's likely to come up, so you should just sort of think going from one side to the other. Now, some of you may have learned how to do this incorrectly in previous classes. Some teachers teach this where you start with both sides of the equation and you manipulate both sides of the equation, try to get it down to an equation that looks like 0 equals 0 or x equals x or something like that. That turns out to be mathematically incorrect. And if you learned it this way, unfortunately, you're going to have to unlearn it, because it's not the way to do these problems. The way to prove an identity is to start from one side and work to the other, whether it's the left-hand side working to the right-hand side, or working from the right-hand side and trying to get to the left-hand side. Here's an example of proving a trigonometric identity. Prove that 1 plus cotangent alpha over cosecant alpha is equal to sine alpha plus cosine alpha. Now remember, the way that we're going to do this is we're going to start from one side and work our way to the other. And typically we start with the more complicated side. In this case, it's pretty clear that the left-hand side is the more complicated of the two. And so let's start with that. 1 plus cotangent alpha over cosecant alpha. Now the question is, what do we want to do to this thing? What substitutions can we make? Now, we can't do any trigonometric, any Pythagorean identities here, because none of these are squared. So right now, there's no reason to think about those things. And so it makes the most sense to take our cotangent and our cosecant and turn them into sine and cosine functions, because in the end, that's what we're looking for. And even if those weren't the things that we're looking for in the end, those will often give us hints as to how things are related to each other, and then we can work our way to whatever result we're trying to get to. So in this case, we'll just start from here. 1 plus cotangent alpha. Cotangent alpha is cosine alpha over sine of alpha. All of this over cosecant alpha. Cosecant is 1 over sine of alpha. Okay, now we take stock again. What do we have? We've got some messy stuff going on in the numerator here. If we want to add them together, we're going to have to find a common denominator. But the more pressing concern is that we have a fraction inside of a fraction. And so typically we try to eliminate the fractions, or at least simplify the fractions, by multiplying by the reciprocal of the denominator. So this is equal to 1 plus cosine alpha over sine alpha times the reciprocal of the denominator, sine of alpha over 1. I could have just written sine of alpha here because sine of alpha over 1 is just sine of alpha, but I'm writing this whole thing in for emphasis. And here is where your algebra experience needs to take over. What we have here is we have parentheses multiplied by something. That tells us we need to do a distributive property. So sine of alpha plus cosine alpha over sine alpha times sine of alpha. Now hopefully you can see what's about to happen here. The sine alphas cancel out. We're going to sine alpha plus cosine alpha. And we can see that we successfully made it to the right-hand side of the equation. And so this is the process for how you would try to prove a trigonometric identity. You start from the more complicated side, try to work your way to the simpler side, and the steps in here are all just substitutions in algebra, and it's just a matter of proper execution. Here's another example. Prove that cosine squared theta over 1 plus sine theta is equal to 1 minus sine of theta. Now again, starting from one side, working our way to the other, and typically starting from complicated, working to simple. This is the more complicated piece. So we'll start here. Cosine squared theta over 1 plus sine of theta. Now in this case, you can see we already have everything reduced to sines and cosines. So that's not the step that we need to take here. Trying to figure out what to do with this is one that takes experience, and one of the things that you will learn is that when you see cosine squared or sine squared, or in fact any of the trig functions squared, it's a callback potentially to the Pythagorean identities. So cosine squared theta, the Pythagorean identity that has a cosine squared theta is this one, sine squared theta, plus cosine squared theta is equal to 1. And so if we rearrange this by subtracting sine squared from both sides, you get cosine squared theta is equal to 1 minus sine squared theta. And so this is sort of our hint as to how we can move forward. We have one of the trig functions squared, and we also can't see anything else to do with it. So here's where we're going to start. 1 minus sine squared theta over 1 plus sine of theta. Now, there is something here that students will do that is algebraically incorrect, but it quote-unquote gets the right answer, which is they try to break this up. 1 over 1, and then minus over plus, sine squared theta over sine theta, because they see that this is where they're trying to get to, so they just sort of say, well, if I do that, it works. It doesn't work. You have to make sure your algebra is valid, and we cannot take a fraction like this with plus signs and minus signs and reduce individual pieces. We have to work with the entire thing. So the question is, how do we get there? What do we need to do? A very common trick with these trigonometric identities, when you have a subtraction here, is that it's actually a difference of squares. This is 1 squared minus sine squared. And so from this, there's a factorization that you should know, which is when you have a difference of squares, this 1 squared minus sine squared, this could be 1 plus sine of theta times 1 minus sine of theta, all divided by 1 plus sine of theta. And now you can see that the 1 plus sine theta cancels the 1 plus sine theta here. And that is how you get down to 1 minus sine of theta. So when you do these problems, again, don't fake it. You have to make sure your algebra is valid, and you have to go carefully, and you just have to make sure that you know what you're doing. And if you're not sure, take your time, ask questions, and just think, am I faking this? Am I just kind of guessing at stuff? Or does it really make sense? And if you slow yourself down enough, you ought to be able to catch when you're faking it with something like this. As we move into right triangle trigonometry, we have to say a few words about how we name the different sides of a triangle. So here we have a diagram. We have an angle theta that's labeled, and then we have names for the different sides. Now the hypotenuse will always be the hypotenuse. It's always the longest side, and it's always across from the right angle. But the other two sides, these are just typically known as legs, and we have to be able to identify one from the other. So relative to the angle theta, we have an adjacent side. It's adjacent to the angle. And then we have the opposite side, which is opposite the angle. So when we see the words adjacent, opposite, and hypotenuse, they always refer to parts of a right triangle relative to some labeled angle. Now when it's labeled this way, oriented this way, this is something that students are pretty familiar with. But as soon as you get a different orientation, students can sometimes struggle with how they want to view these things. So let's call this angle here alpha. There's your right angle. Where's the hypotenuse? Now some students will say hypotenuse and they'll look for this sort of lower left to upper right diagonal and label this the hypotenuse, and that's just not how it works. Hypotenuse is always relative to the right angle. It's the longest side and it's always across from the right angle. This side right here, that's the adjacent side because it's adjacent to the angle, which makes this one the opposite side. Now this isn't particularly confusing if you take your time, but if you go too quickly, you might make mistakes. And there's something else that happens, which is that these names are relative to the angle. So if we call this angle here beta, all of a sudden some of these names are going to change. The hypotenuse will still be the hypotenuse, but now this side over here is opposite. It's the opposite relative to the angle beta. And this is the adjacent side, and it's adjacent relative to beta. So always keep in mind that adjacent and opposite are relative to the angle that you have labeled, and there are problems where you're going to have to interact between two different labels, and that's just how it is. So pay attention and take your time with these things. Earlier, we had defined the trigonometric functions in terms of points on a plane. It turns out that there's a way to use right triangles to talk about these things, and this is known as right triangle trigonometry. So SOHCAHTOA. This is the term that most students remember. It's just a mnemonic device. It's just a bunch of syllables that kind of sound good together. And so SOHCAHTOA, this is how students remember this. What does it mean? Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So that's a SOHCAHTOA. And all it says is that if we take these these parts of the right triangle relative to some angle, we can actually set up relationships that give us these different trigonometric functions. And we'll see later how these relate back to the formulas we used using points on a plane. So here's an example. Determine sine of alpha, cosine alpha, and tangent of alpha given this diagram. Now the first thing you'll notice is that the alpha is labeled here, but the hypotenuse is across the bottom. We don't know the length of the hypotenuse, so maybe that's the first thing we should start with, because we're going to need all three sides to calculate these values. So we can use the Pythagorean theorem. We'll just call this thing c. So c squared is equal to 4 squared plus 7 squared. 4 squared is 16. 7 squared is 49. 16 and 49 is 65. So c is the square root of 65. So we can label that. Excuse me. Now we need to do sine, cosine, and tangent of this angle here. SOHCAHTOA. Again, a bunch of meaningless symbols that remind us what the relationships are. So sine of alpha is the opposite over the hypotenuse. Now in this case, here's our angle alpha. The opposite side is 7. And the hypotenuse is the square root of 65. Right, so again, the hypotenuse is the longest side down here. Cosine of alpha is adjacent over hypotenuse. So the adjacent side, adjacent to the angle, is 4. And the hypotenuse is square root of 65. And lastly, tangent of alpha. Tangent, the TOA, is opposite over adjacent. So the opposite side is 7, and the adjacent side is 4. So using SOHCAHTOA to calculate sine, cosine, tangent of a particular angle in a right triangle, it just comes down to labeling it correctly and then not making mistakes when you set up these relationships. Now at this point we have two different presentations of the sine and cosine function. We have the sine and cosine functions in terms of points on a plane, and we have the sine and cosine functions in terms of these right triangle relationships, and of course tangent comes along through the relationships that we've set up. And so the question is, how do these things all match up? So let's start by drawing a picture that corresponds to this, the points on the plane. So we have a point xy in the plane. The distance r is the distance from the origin to that point, and that creates an angle theta. Now, in order for us to make this picture look like this picture, what we have to do is we have to create a right triangle by simply dropping that point down to here to create that triangle. Because now if we think about it, x corresponds to the horizontal distance to the point, and y corresponds to the vertical distance to the point. And we can see that we have a right triangle labeled. Y over r, y over r. Well, this is the opposite side, and that's the hypotenuse. Sine is y over r, sine is opposite over hypotenuse. And you could work your way through. Cosine is x over r, x, well that's the adjacent side, r is still the hypotenuse. So cosine theta is adjacent over hypotenuse, which is what we have here. Tangent theta is y over x, here's y, here's x, opposite over adjacent. Tangent theta is opposite over adjacent. And so this shows us how the two pieces actually fit together into one. It's just a matter of creating a right triangle picture out of our points. You could have also done this the other way around. You could have started with a right triangle and then simply embed it into the plane. And as long as you set it up with the angle in the appropriate place, you will get the same relationships out of this. Now there is one thing to say about this, which is that this relationship right here, this only works within the triangle, which means that this only works for acute angles. These definitions work all over the plane. And so there is a little bit of difference, but this just shows that they represent the same concepts. We're going to take a look at the cofunction identities for the sine and cosine functions. That's what these are right here. Sine of pi over 2 minus theta is equal to cosine of theta, and cosine of pi over 2 minus theta is equal to sine of theta. Now there are actually other cofunction identities using the other trigonometric functions, but they all have the same basic shape, and they're all proven by the same basic method we're going to have here. So we'll just keep our focus on the sine and cosine functions. So there are a couple of things we need to think about as we get started. The first one is, what is this angle pi over 2 minus theta, and how does this fit in with theta? So if we have a right triangle like this, we're going to label this other angle over here alpha. And what we need to think about is, what is the relationship between alpha and theta? Well, we know that the sum of the angles in the triangle all add up to 180 degrees. Now we're going to do everything in radians because it's good practice. So all the angles add up to pi radians. So theta plus alpha plus this right angle, a right angle is pi over 2, is equal to pi. Again, all in radians. Let's rearrange this. Let's subtract off the pi over 2 from both sides. Theta plus alpha is equal to pi over 2. Now remember, pi over 2 is 90 degrees, and you might remember that there's a word associated with two angles that add up to 90 degrees, add up to a right angle. These are known as complementary angles. And so this formula right here tells us that theta and alpha are complementary angles. But we can go one step further, and we could solve for alpha. Alpha is equal to pi over 2 minus theta. And this right here is what appears up here. So what's happening with this formula is that it's saying that the sine and cosine functions on the different acute angles within a right triangle are related to each other. And now we just need to figure out why. Why is this the thing that works? So I'm going to start labeling the sides. So relative to theta, this is the hypotenuse, that's the adjacent side, and that's the opposite side. But remember that the labels change depending on whether you're looking at it relative to this angle or that angle. So let's take a look here. So relative to this side, well, hypotenuse will always be the same. This over here is the opposite relative to alpha, and this is the adjacent relative to alpha. And so let's take a look at the first one. Sine of pi over 2 minus theta. Okay, sine of pi over 2 minus theta. That one's the alpha. Sine of alpha. Sine of alpha, sine SOHCAHTOA. Sine is opposite over hypotenuse. So the red opposite over the hypotenuse for this left-hand side here. Right-hand side, cosine of theta. Cosine is adjacent over hypotenuse. So relative to theta, we have adjacent over hypotenuse. And what we can see is that even though the names are different, the thing that they refer to, the actual part of the triangle that they refer to is the same. The red opposite and the green adjacent are the same side. They have the same length, and the hypotenuse is always the hypotenuse. And so what this is saying here is that the sine of the other angle in the right triangle is the cosine of this angle. So there's this sort of interchange between the two functions. So anyway, these are the cofunction identities. You can do the same thing with the cosine of the sine. You'll just see that instead of here, you'll have adjacent over hypotenuse and opposite over hypotenuse in the appropriate colors. And so this shows us how these cofunction identities work and why they are what they are. The next thing we're going to look at is solving triangles. Now specifically we'll be solving right triangles in this section, and later on we'll solve general triangles. To solve a triangle means to determine the lengths of the sides and the measures of the angles. So what's going to be happening is that you're going to be given, in this case, a right triangle, and you're going to have some information about it. Now the specific information you'll be given will depend on the problem. Sometimes you'll be given two sides, sometimes you're given a side and an angle. You just don't know. So for this case, I'm just going to label this one and this right here. And so from this information, we're supposed to get all the other sides of the triangle. Now for convenience, we tend to use a notation that helps us organize our information. So A is across from the angle alpha, use B across from the angle beta, and C for the hypotenuse. It's not always like this, but being consistent with your labeling will help you avoid mistakes. And so the question is, well, what techniques do we have to use with this? Well, there are two things. First thing is that we have the Pythagorean theorem. A squared plus B squared equals C squared, right? The sum of the squares of the lengths of the legs of the triangle, right triangle, is equal to the square of the length of the hypotenuse. So A squared plus B squared equals C squared. This helps you determine the length of the third side if you're only given two of the sides. Otherwise, you're going to have to use the trigonometric relationships, SOHCAHTOA. From this, knowing the sine and cosine functions of various angles, you will be able to determine the other, you'll be able to set up equations that will help you determine the other sides. Now, when you do this, if the angle is a known value from the unit circle diagram, you should use the exact value, meaning you should use the square root of 3 over 2 or the 1/2 or the root 2 over 2. Those values, when you're given the angles of 30 degrees or 60 degrees or 45 degrees, those are the ones that you should be using. You should not be using a calculator for those numbers. If you're given other values like 37 degrees, 15 degrees, 18 degrees, then you can go and use a calculator. It's really important when you use a calculator, make sure you know what mode it's in. Calculators can do your computations in degrees or radians, and you have to make sure you're in the appropriate units for the calculation that you're doing. So please keep an eye on that. So here's an example. Solve this triangle. Now remember, solving a triangle means finding the lengths of all the sides and determining all the angles. Now I'm going to make a little chart here off to the side. We have 3 angles that we need, and we have 3 lengths. And it's going to be helpful for us to label this, so I'll label the known side A, B is the other leg, and C is the hypotenuse. Again, keeping consistent with previous notation. And that would make this angle here alpha, this one beta, and that one gamma. So we already know some information. We know A is equal to 6, we know alpha is equal to 30 degrees, and we know gamma is equal to 90 degrees. So the first thing we might want to do here, since we know two of the angles, is determine the third angle. And this comes from the fact that the sum of the angles of the triangle equals 180 degrees. So I'll write it out. Alpha plus beta plus gamma equals 180 degrees. We know alpha, 30 degrees. We know gamma, which is 90 degrees. And so we can plug those in, and if we subtract off 90, we subtract off 30, we get beta is equal to 60 degrees. Now you might have also been able to recognize that this is a 30, 60, 90 triangle just from these two sides, knowing that it's a 30 and 90 there. But this is how we would do it in general, just in case it's not one of those known triangles. So that's the first part of this. We now have all three angles. We need to work on the other two sides now. Let's focus on side C for a moment. So we know that this side has length 6, and we are interested in finding the hypotenuse. And we're going to have to pick one of the trigonometric functions to work with. Focusing on this angle alpha, focusing on this 30-degree angle. What is that side relative to the 30-degree angle? That is the opposite side. This side, C, is the hypotenuse. Opposite hypotenuse. Which trigonometric function relates opposite to hypotenuse? Since it's the sine function, we can take this formula right here and plug things in. So sine of 30 degrees is equal to opposite, which is 6, over the hypotenuse, which we don't know, that's C. From this, we now need to think, well, what is sine of 30 degrees? Sine of 30 degrees, you have to go back and think about the chart of values from the unit circle. Sine of 30 degrees is 1/2. So 1/2 is equal to 6 over C. And if we solve for C, we multiply both sides by C, multiply both sides by 2, we get C is equal to 12. Now, you could have also done this because this is a 30, 60, 90 triangle. You know that the shortest side is half the length of the hypotenuse. That's part of the 30, 60, 90 relationship. But again, we're doing this to sort of set things up in general. So then the last part would be to calculate B. And there are a couple different methods. We can just solve for B using this a relationship like this. We could use the cosine of alpha, or maybe even if you want to switch it up, you can use sine of beta, or you could even use the tangent function. Alternatively, you could use the Pythagorean theorem, a squared plus b squared equals c squared. And so I'm going to stick that right over here. Let me switch sides. So a squared plus b squared equals c squared. Our a is 6. So 6 squared plus b squared is equal to, our c was 12. 6 squared is 36. 12 squared is 144. Subtract off. B squared is 108. So b is equal to the square root of 108. Now this is acceptable as it is. We should check to see whether it reduces. We can see that it's divisible by 9. And so there's at least a factor of 3 that comes out. So let's see, let's do the calculation here. 108 is 3 times something, 3 times 36. And so we have 36, oh, well 36 is already square. So we could just do 6 square root of 3. So square root of 108 is square root of 3 times square root of 36. Square root of 36 is 6, so 6 square root of 3. And so the third side is 6 square root of 3. And again, because it's a 30, 60, 90 triangle, you could have done that by just remembering the ratios between the various sides. But it's important to see the big picture as well. Here's a typical sounding word problem involving solving parts of a triangle. From a point 30 feet from the base of a tree, the angle from the ground to the top of the tree is 57 degrees. Determine the height of the tree. All right, so what's going on? Well, let's draw a little diagram. There's our tree. We are at a point 30 feet from the base of the tree. So 30 feet this way. So we're 30 feet away from the tree. The angle from the ground to the top of the tree is 57 degrees. determine the height of the tree. So we'll label the height of the tree h. That's our variable that we're trying to determine. So we don't need all the parts of the triangle in this case, we just need h. And so what do we think about? Well, we have an angle. We have this side and that side. We have the opposite and the adjacent side. Which trigonometric function relates an angle to the opposite and adjacent sides? So you think through SOHCAHTOA, and you should end up with the tangent of theta is the opposite over adjacent. And so all we need to do is take these values and plug it in. Tangent of 57 degrees is equal to the opposite, which is h, over the adjacent, which is 30. Now, I would push back against plugging this into the calculator right away. Sometimes when students do that, you start to introduce rounding errors, and then especially if the problem's longer, those errors propagate forward and make your final answer less accurate. So it's best, I think, to keep this in its exact form until you need to plug it into a calculator. So let's go ahead and leave it like this. We want to solve for h. We're going to multiply both sides by 30. So h is equal to 30 times tangent of 57 degrees. Now, this is an exact value for h. Just like when we were working with the pi values when we were talking about circles, in a practical situation, this is not helpful. This does not actually tell someone how tall the tree actually is. And so this is where you then go to your calculator and plug it in. Very important, when you do this, make sure your calculator is in degree mode because we're working in degrees and not radians. This is just something you have to check. It's just be diligent about it. When you plug this into a calculator, you're going to get that this is about 46.2 feet. Right, and of course, this number 46.2 is way easier to understand than 30 times tangent 57 degrees. So this is how we solve this problem. We actually have determined the height of the tree based on how far away we are from the base and the angle up to the top of the tree, and it comes out of the SOHCAHTOA relationships.